In the fourth video on substitution alpha-2 carbonyl compounds, we are going to examine alkylation of carbonyl compounds. So we are going to look at first deprotonation of carbonyl groups, then alkylation of enamines, acetoacetic and malonic ester synthesis, and finally we are going to examine use of these reactions in formation of carbocyclic rings. A deprotonation of carbonyl group can be carried out under kinetic or thermodynamic conditions. And frequently we carry it out under kinetic conditions because that's more advantageous, and we use a very strong base, lithium diisopropyl amide or LDA. So let's look at deprotonation under equilibrium conditions or quantitative deprotonation. So under equilibrium conditions, deprotonation occurs when we use what we would consider to be typical strong base, what we call strong base, such as hydroxide, sodium or potassium hydroxide, or maybe corresponding alkoxides like sodium methoxide, sodium ethoxide. In that case, we have an equilibrium, and actually equilibrium is to the left. So most of the material at equilibrium is in the form of carbonyl compound and hydroxide. A very small amount is deprotonated carbonyl compound, inlet anion, and of course water. That's because of the relative pKa's. You can see that water is much stronger acid compared to starting carbonyl compound, in this case acetone. So under equilibrium conditions, or so-called thermodynamic conditions, we have very small amount of deprotonated species. Nonetheless, this deprotonated species, as you have seen in the previous videos, readily undergoes reactions, and that's because of the Le Chatelier's principle. As soon as some of the deprotonated species is taken out of the equilibrium, more is deprotonated to reestablish the equilibrium, and so on. Deprotonation continues until all of the material is used up. Now, what is more commonly carried out when we want to deprotonate carbonyl compound for purpose of, for example, alkylation, is reaction with LDA, lithium diisopropyl amide. And formula of lithium diisopropyl amide is shown here. That's an exceptionally strong base. Such a strong base quantitatively deprotonates carbonyl compound. And so, since deprotonation is quantitative, simply equilibrium is to the right. So a reaction occurs under kinetic conditions, and all of the carbonyl compound is converted to corresponding inlet anion, in this case lithium inolate. And that's simply because we are using such a strong base, LDA. You can see its conjugate acid, diisopropyl amine, has pKa of 35. Deprotonation of unsymmetric ketones proceeds in different manner using LDA or sodium hydroxide, so under kinetic or thermodynamic conditions. Under kinetic conditions, less hindered proton is removed. So in this case we have 2-methyl cyclohexanone, and of course position 6 is less hindered compared to position 2. Position 2 has methyl group, and so that's more hindered proton. LDA, as you can see from the formula, has 2 isopropyl groups, so it's hindered base, and also since reaction occurs under kinetic conditions, less hindered proton is removed. So inlet anion is less substitute inlet anion. That's actually less stable inlet anion, because double bond has fewer substituents, so that's less stable carbon-carbon double bond. Under thermodynamic conditions, since these are equilibrating conditions, more stable inlet anion forms. And more stable inlet anion is one where double bond is more substituted. So in this case, double bond forms between carbons 1 and 2 of cyclohexane ring. And so it's more substituted double bond. So two bases exhibit different regioselectivity when it comes to formation of inlet anion. And to alkylate ketones and esters, we typically carry out reaction under kinetic conditions. So we first deprotonate carbonyl compound with LDA. Typical solvent for LDA is THF, tetrahydrofurane, and we carry out reaction at very low temperature, minus 78 degrees Celsius. That's a dry ice acetone bath. So after deprotonation, we add alkyl halide, and then in SN2 reaction, inlet anion displaces halogen to give alkylated product. And here is the reaction mechanism. So first step is kinetic quantitative deprotonation. In this case, acetone is deprotonated to give inlet anion. And then in the second step, we have SN2 reaction. So inlet anion in backside attack displaces halogen, in this case bromide anion, to give the final product, in this case 2-pentanone, and bromide anion as a leaving group leaves. Nitriles can also be deprotonated at alpha position. They have properties similar to carbonyl compounds. So LDA deprotonates nitrile in alpha position, and then this anion, again in SN2 reaction, can displace halogen atom to give corresponding alkylated product. Esters also can be deprotonated with LDA in alpha position, and you can see this rather complex bicyclic ester. So LDA deprotonated in alpha position, and then iodomethane is alkylating agent. So iodine in SN2 reaction is displaced by carbonyl. Now, under thermodynamic equilibrating conditions, reaction doesn't proceed that well. And the reason for it is that conditions are equilibrating. So first, small amount of inlet anion forms, and that inlet anion will be alkylated. So inlet anion will react, for example, with iodomethane, and iodine will be displaced, so carbon bond will be made. But once that anion reacts to give, in this case, dimethyl compound, then new anion will form. So that alkylated compound will give new anion, and that new anion will again get alkylated, and so on. In addition, while preferentially more substituted inlet anion forms, it's only preference for it, not exclusive formation of more substituted inlet anion. So some of the less substituted inlet anion forms, that one also undergoes reaction. So typically we get complex mixture of products, and the ratio of these, in this case I have shown 4 products, there could be more, but the ratio of these products depends on a number of factors. Stoichiometry could depend on reaction temperature. So typically we get pretty bad mixture, and often trialkylated product is one that predominates. But since they are obtained in low yield, they are impure, and they are difficult to separate from each other, this reaction is not considered to be of preparative value. So typically we carry out reaction under kinetic conditions as shown here, for example on methyl propanoate. So with LDA it's deprotonated, and then reaction with bromoethane gives corresponding alkylated ester. Cyclic esters, lactones, react just as well. So LDA deprotonates this lactone in alpha position, and then reaction with allyl bromide introduces allyl group in alpha position. Another class of compounds that are very useful in alkylation reactions are enamines. Enamines are amines, that means alkene amines, and they readily undergo reaction with electrophiles, and that's shown here. Mechanism is shown right here. So carbon-carbon pi electron pair is readily donated to form bond with an electrophile because leaving of it is assisted by free electron pair from nitrogen. That gives ammonium cation, which readily hydrolyzes upon treatment with water to give alkylated carbonyl compound. So enamines are very useful. First, they are easy to prepare, and reaction conditions are rather mild. Unlike LDA, which is expensive, and we have to carry out reaction at -78, in this case we can carry out reaction at room temperature. The only problem, relatively minor problem, is that we have to exclude moisture. But in general, we have to exclude moisture also when dealing with base such as LDA. With moisture, of course, enamines readily hydrolyze to carbonyl compounds. And here is another quite common use of enamines. So typically, to prepare an enamine, we would use something like morpholin. So this cyclic compound that has oxygen and NH group in 1,4 positions is called morpholin. Its trivial name is morpholin. So under acidic conditions, reaction with carbonyl compound gives the corresponding enamine. And then that enamine, upon treatment with an alkyl halide, in this case bromoethane, is alkylated to give the corresponding ammonium cation, and then upon treatment with water we get alkylated product, alkylated ketone, in this case 2-ethyl cyclohexanone. Typically alkylation proceeds in excellent yield, products are very pure, so this is very useful way to alkylate ketones through intermediate enamines. Another way to carry out alkylation of carbonyl compounds is to use a dicarbonyl compound, a beta-dicarbonyl compound. Unlike monocarbonyl compounds, such as aldehydes, ketones, esters, which upon treatment with alkoxide or hydroxide give equilibrium of protonated and deprotonated species, and at that equilibrium, deprotonated species inlet anion is present usually in very small amounts, typically less than 1%. Dicarbonyl compounds are quantitatively deprotonated upon treatment with hydroxide or alkoxide. And since deprotonation is quantitative, then this is a very useful method for alkylation. The reason for it is, of course, high acidity of dicarbonyl compounds. In this case, we have methylene group, and that methylene group is activated by two neighboring carbonyl compounds. That makes it very acidic. Those protons are very acidic. And so pKa of that group, depending on carbonyls, is somewhere between 5 and 9, which is much higher than, let's say, pKa of water, 15.7, which means that hydroxide will easily quantitatively deprotonate it. So reaction is now kinetic. It's no longer thermodynamic, and alkylation occurs really easily. So typical compounds are beta-Ketoesters. This particular beta-Ketoester is ethyl acetoacetic ester. Of course, again, as we have encountered that before, base has to be the same as the leaving group of the ester. So etoxy is the leaving group of the ester, or etoxide, so etoxide has to be a base, and that base has to be used in the corresponding solvent, that means ethanol, corresponding alcohol. Upon deprotonation, anion is obtained, and that anion in SN2 reaction displaces bromine from ethyl bromide to give alkylated product. So this was beta-Ketoester. Malonic acid diesters are beta-diesters. So this is diethyl malonate, and they are also easily deprotonated. Methylene carbon is easily deprotonated. So again, we use etoxide in ethanol and to give a corresponding inlet anion, and then reaction with iodomethane introduces methyl group on the middle carbon, on the methylene carbon. Now, often we don't need dicarbonyl compound in the final product. We actually need the monocarbonyl compound. So we need to get rid of one of the carbonyl groups. And as it happens, when one of the carbonyl groups is carboxylic group, beta to another carbonyl, that one is easily removed because these compounds are unstable upon heating. So heating of acetoacetic acid, this is acetoacetic acid, where carboxyl group is beta to a carbonyl, to a keto group, gives acetone and carbon dioxide. So carbon dioxide is lost from the carboxyl group. In case of the acid, malonic acid is unstable upon heating. Upon heating, it loses carbon dioxide from one of the carboxyl groups to give acetic acid. And here is the mechanism. It's easier to draw the mechanism if you rotate carboxyl group on the right. Then you can see that there is a 6-membered cyclic transition state. So this is concerted reaction, and it's pericyclic reaction. Concerted, there is only one step, no intermediates. Pericyclic, there is cyclic transition state. And you can see how bonds are formed. Curved arrows show bond formation. So electron pair from oxygen forms bond through hydrogen. They were already, as you can guess, close to each other and formed a hydrogen bond. So in this case, simply we go from hydrogen bonding to actual covalent bond. Hydrogen, of course, cannot form two bonds. That will result in breaking of the other OH bond. That OH electron pair now forms carbon-oxygen pi bond, and That results in formation of molecule of carbon dioxide, very stable molecule which bubbles out of the solution. Of course, as molecule of carbon dioxide is formed, that results in breaking of carbon-carbon bond, and that electron pair forms another carbon-carbon pi bond, and at the end enol. So initial products of this reaction of decarboxylation of acetoacetic ester are enol form of acetone and carbon dioxide. Enol form, as you know, is unstable and tautomerizes to corresponding keto form, to a molecule of acetone. The same mechanism operates with malonic acid. Again, same pattern of bond formation and bond breaking occurs. It's concerted pericyclic reaction, and upon heating, products are enol form of acetic acid and the molecule of carbon dioxide. Enol form of acetic acid is unstable and tautomerizes into acetic acid. So to alkylate a ketone or an ester or an acid, we carry out these two steps in sequence. And when we do that, then that's called acetoacetic ester synthesis or malonic ester synthesis, depending on what is the starting material. So we often don't need two carbonyl groups in the product. We only want alkylation of monocarbonyl compound. But since alkylation of dicarbonyl compound is much easier, we alkylate dicarbonyl compound, remove one of the carbonyl groups, ester group as carbon dioxide, and end up with alkylated carbonyl compound. So here is an example of acetoacetic ester synthesis. So this is methyl acetoacetate. We deprotonate it with corresponding base, methoxide, like sodium methoxide in methanol, that generates carbanion, inlet anion, and then in SN2 reaction with alkyl halide, it is alkylated in the methylene position, carbon atom between the two carbonyl groups. Finally, acid-catalyzed hydrolysis hydrolyzes acetoacetic ester to acetoacetic acid. And acetoacetic acid is unstable upon heating. It loses carbon dioxide to give the corresponding alkylated ketone. So in this case, we have been able to carry out alkylation very cleanly and in very high yield under relatively mild conditions and using inexpensive reagents without having to worry about moisture or low temperature or using expensive reagent like LDA. So this is often method of choice for alkylation of ketones as opposed to using LDA. And here is an example of alkylation of malonic ester or malonic acid diester. So diester of malonic acid is deprotonated by the corresponding alkoxide in the alcohol. That results in formation of inlet anion, and then reaction of that inlet anion with alkyl halide results in alkylation of methylene carbon. Finally, hydrolysis under acidic conditions, acid-catalyzed hydrolysis, with heating results in loss of, first in hydrolysis of diester to diacid, and then loss of carbon dioxide to give corresponding alkylated acid. So product is corresponding alkylated acid. And as before, reaction conditions are relatively mild, and reaction is easy to carry out. It's carried out at room temperature and then with heating. And in general, it's much easier to carry out reaction with heating than with cooling. So if you have a choice, you'll prefer to do reaction with heating than with cooling. And we avoid use of expensive reagents such as LDA. Here is the reaction mechanism of particular specific reaction, diethyl malonate. So with ethoxide as a base, like sodium ethoxide, it's deprotonated in methylene position, so inlet anion, then reacts in SN2 reaction with, in this case, 1 bromopropane, SN2 reaction, so alkylation of methylene carbon occurs, so new carbon-carbon bond is formed. Then under acidic conditions with acid catalyst, diester is hydrolyzed to corresponding diacid, malonic diacid, and upon heating, molecule of carbon dioxide is lost, as we have seen in the previous mechanism, to give alkylated acid. And so in this case, from malonic acid, we have made pentanoic acid. This reaction can be also exploited in formation of carbocyclic rings. Carbocyclic rings with single carbonyl group. We already know Dickmann condensation, that's intramolecular Claisen condensation. So diesters can cyclize to form rings. The cyclization of such diester produces beta-Ketoester. And usually we don't need beta-Ketoester. Usually we need a cyclic compound that has just one carbonyl group, like cyclopentanone, cyclohexanone. There may be some other substituents elsewhere on the ring. But we usually don't need ester group. So right now we can easily get rid of it. So by now, given what we have covered, you know how we can remove this ester group. So first, acid catalyzed hydrolysis. Hydrolysis beta-Ketoester to beta-keto acid, and then beta-keto acids are unstable, so upon heating they lose carbon dioxide to give corresponding ketone. Another method to form rings is dialkylation of beta-Ketoesters or malonic acid diesters. Dialkylation with dihalide. And by doing this dialkylation, we can actually prepare rather small rings, because this reaction is kinetic. So it's not thermodynamic, rings cannot undergo ring opening, and so we can actually prepare rather small rings. In this first example, we have methyl acetoacetate, so deprotonation with methoxide in methanol, and then reaction with 1,3-dibromopropane results in first alkylation of first substitution of one bromine, and then methoxide deprotonates, resulting intermediate again to form second inlet anion, which displaces second bromine and results in closing of four-membered ring. And then, of course, acid catalyzed hydrolysis followed by heating results in decarboxylation, and product is this four-membered ring with keto substituent on it. Here is the mechanism. Here are details of the mechanism. So first step is deprotonation to give inlet anion, and then in SN2 reaction, this inlet anion forms carbon-carbon bond. In the next step, resulting intermediate is deprotonated again, so there is one more acidic proton left, so that second acidic proton is removed, and then inlet anion in intramolecular reaction now displaces bromine to form four-membered ring. That compound with four-membered ring in the final step is hydrolyzed, so acid catalyzed hydrolysis of the ester, and upon heating carbon dioxide is lost to give this cyclobutyl ketone, cyclobutyl methyl ketone. So that's the proper name, methyl cyclobutyl ketone. And we have reached the end of this chapter. So this completes chapter on alpha substitutions of carbonyl compounds. And in the next chapter, we'll be covering polymers.